Okay, so welcome everybody to the very last talk of the series in this semester. It'll be given by Vincent Lam, who studied physics and philosophy just up the road from here in Lausanne, where he also got his PhD in philosophy under the supervision of Mr. Esfeld. After that, Vincent moved to Australia, to the University of Queensland, to do his postdoc there. Came back to Switzerland to do another postdoctoral fellowship in Lausanne, and then now moved to Geneva and is a scientific collaborator here. Next year, he will move to the University of Bern and be a junior professor there at the University of Bern. He published widely in philosophy of physics, philosophy of science, physics, and has a book forthcoming with Daniele Oritti on group field theory and its philosophical foundations. So very pleased to have him here today. He will be talking about perspectives from general relativity and quantum gravity on laws of nature and causation. Please, Vincent.
Yeah, thank you, Chris.
You're going to take the place apart.
Yeah, it's a pleasure to present this to you all. This talk has different parts, 3 different parts, and you'll see the different aspects. It's not different levels. We'll see this. So first, the aim, the global aim of this talk is to articulate a set of metaphysical conceptions about laws and causation in the context of GR, and then beyond in the context of quantum gravity. And it aims to be an example of how current phenomena of physics may contribute to debates in metaphysics. So, kind of case for scientific metaphysics. So, as I said, there are 3 parts to this talk. The first part is going to be about the spatial aspect of the standard conceptions, about laws and causation, and in particular we'll focus on the global constraints, the global topological constraint that one might want to impose in order to define non-human conceptions about laws. In the second part, I will more specifically focus on counterfactuals in dynamical space-time, and in particular the initial value formulation of GR. And in particular, I will highlight subtleties coming from the non-linearity and the ellipticity of the constraint structure there, raising some difficulties for evaluating counterfactuals in this context. And in the final part, I will address the issue of how to update these conceptions in the context of quantum gravity, where space-time might not be phenomenal. Okay, let's start with the first part. So the framework here is a realist framework. So I take laws and causation to be about objective features of the world. And the conceptions I'm considering here are dividing along the following lines about whether or not these features irreducibly include nomic facts in the world, or whether we can reduce them to non-nomic, non-modal, non-causal facts. So we have two families here in this, according to this division. First, the reductive conceptions, for instance, humanism about laws and causation, and the non-reductive conceptions, like, for instance, dispositionalism or primitivism about just taking laws as being something definitive in your ontology. And now I just want to highlight, I won't expose these metaphysical conceptions in details. There are many papers, huge research areas on these conceptions, but just want to emphasize here the space-time aspects of these conceptions. For humanism, it's pretty obvious. Laws and causation are reduced to, supervene in some technical sense, on the entire space-time distribution of phenomenological, particular, non-modal, non-nomic, non-causal facts. Okay, we have the whole human mosaic. And typically laws are then understood to be supervening on this mosaic, just in terms of regularities or patterns. of this mosaic. For instance, there is a system analysis. And causation, similarly, supervenes also on this mosaic. For instance, then understood in terms of a counterfactual analysis. That's the reason why then in the second part I'll focus on counterfactuals, because they really play an important role there. And in the second family of conception, I'm considering here primitivism, dispositionalism. The space-time distribution of practical facts is determined by initial conditions of the world, together with primitive laws, or by the fundamental dispositions, the nature of the properties, instantiated by the initial state of the world. And then laws typically understood either as just being obviously primitive, or as being grounded in the irreducible fundamental nature of the properties, which is then dispositional. And causation is then, in the first case, closely linked, ontologically linked to laws, or just somehow taken as primitive, as being linked to the nature of properties. The nature of properties then is typically taken as being causal. Now I'd like to emphasize the more temporal aspects of these conceptions. I've taken as an example Morgan's primitivism about laws. So he's one of the proponents of taking laws of nature as fundamental. He has a few quotes from his book, Metaphysical and Physics, the chapter on the Water's proposal. Here is what he says. The issue of time and the issue of natural laws are deeply entwined. The fundamental laws of nature appear to be laws of temporal evolution. They specify how the state of the universe will or might evolve from a given initial state. Here we see that the law really, there's this notion of production and governing. They govern the temporal evolution of things. Okay? The temporal state of the universe is, in a certain sense, derivative. It is the product of the operation of the laws on the initial states. Okay, that's a good feature of this, according to Morgan, of this view. You don't need to accept the whole mosaic. Okay, you only need to accept an initial surface, for instance, like the surface in GR, and then all the rest of the mosaic is derivative. The laws of temporal evolution operates from that initial state to generate or produce. Okay, there's this production notion. Later states, and the sum total of all the states so produced is the human mosaic. Okay? Again, you don't need to accept the whole human mosaic. In this conception, of course, time is fundamental. Okay? It's dimension in which laws operate. So you have the laws as fundamental, and of course, time. And of course, more specifically, the notion of directionality field. It's very similar in the case of dispositionalism about laws, where, again, fundamental physical properties are understood in terms of their irreducible, powerful, dispositional nature to produce certain effects, and properties are understood in terms of what it does. Laws and causation then are locally encoded. This is important in the very nature of the properties. Okay? To understand the law of nature and causation, you don't need to look at all the regularities or the patterns in the whole mosaic and the entire space-time distribution of facts. All you need to look is the particular property and what it does. And the law then and the causation is grounded in the nature of this property, typically in this kind of case. You don't need to look at the whole distribution again. But clearly here, this notion of production, like in the Morgan's view, it's clearly temporal aspects. The whole space-time distribution of fundamental facts, mosaic, is produced by the fundamental dispositional properties, typically at an instant of time, take the initial state of the world. And in this sense, the human mosaic is derivative. Okay, this is the kind of ontological aspect of production. And again, this is taken as a good feature of this conception. You don't need, again, to accept all these regularities, all distribution of all the facts at all times. Now, about the temporal aspects of the typical human conception, time can be taken just as part of the representation, the kind of parameter which appear in the best system. Okay. Best system in the sense of Lewis, kind of best combination between simplicity and explanatory power. But still, it's interesting to see that in recent work on the humanism, like the work of Ed Hall, it seems that time does play some kind of role. He argues, for instance, that the best system should encode a kind of distinction between what he calls an initial condition hypothesis and a dynamical hypothesis. And the initial condition hypothesis is a set of non-logically possible initial conditions And this should be uninformative. Okay, you should be able to accept as many initial conditions as possible. If your explanatory power is just because of the fact, so to speak, that you just restrict the possible initial conditions, then it's not explanatory helpful in this sense. Should I do something? Wait, just wait. Do you hear me?
Yeah.
Okay, good. Very good. And so there is this initial condition hypothesis and the dynamical hypothesis, which is the specification of how the initial conditions evolve forward in time. And this, of course, the explanatory power should be in this part, not in this, not the initial conditions. It seems quite reasonable. And it's interesting to see that in the end, maybe the time might play some role even for human conceptions. Now, the GR context, space-time is dynamical, in the sense that space-time geometry and gravitation are the same dynamical structure, okay? The differential fields and financial equations. And these equations are not explicitly temporal evolution equations. Okay? You have to massage them in order to put them into a hyperbolic form. And there is no fixed non-dynamical space-time background with respect to which the temporal evolution can be defined. But still, you have the local Lycombe structure as defined by the metric. But because of the dynamical aspects, you can have non-trivial global topologies. And typically, the theory allows for CDCs, closed time-like curves. It's very easy to generate such curves. It is a well-known example, just a space-time, you roll the space-time up and you get a closed CDC. More fancy example like Taylor space-time. But yeah, the details are not relevant here. It's nice. Now, it seems clear that there is a tension between the non-human conception of counterfactuals and these non-trivial global topologies. Here's what Morgan says: production is clearly transitive. So production in a circle would imply self-production, but the nighttime cannot be the ontological ground of its own production. This means that the existence of CDC would imply the non-existence of the source of productive explanation and might suggest that the human account is the strongest that can be had. So if he seems to be saying that if we have CDCs, if we allow for CDCs or this kind of global topological features, then it seems that humanism would be better. But of course, for him, a possible move is always, and that's more or less what he does, to exclude space-times, the cities as unphysical, typically by imposing global topological constraints. That's a possible move for him. But now I just want to briefly look at what this would amount to. Typically, we could put a constraint on the theory. This is not part of the theory itself. It's an additional constraint that we put on the theory, that it has no CDC. It's called the chronological condition. You can put this on your manifold. But you need more for primitivism and disposition, as we've seen this. We need this notion of state of the world at a time, initial state of the world, initial conditions, from which later states of the universe are produced or evolved. So this requires stronger global conditions, typically a notion of global time function, typically a function which increases along all causal curves, future clarity causal curves, that's the idea. And we need this notion of the universe at the time, being encoded by the notion of Cauchy surface, typically a space-like hypersurface tree, hypersurface, acronorm and so on, which got every inextendable causal curve exactly once. That's the idea of Cauchy surface. This would encode this notion of the universe at the time in GR. But there is actually, if you go into the details, there is a hierarchy of such causal conditions that can impose. I'm not going to discuss this in details now. We can in the presentation, but the idea is to show you that these are about global features of space-time, and there are a hierarchy of such conditions. You can impose to have not closed timeless curve, no closed causal curve. You have distinguishability conditions, strong causality condition, and stable causality conditions that if you slightly open up the light cones, then you don't get CPCs. And there are interesting results, typically, that the stable causality is equivalent in a precise sense to the existence of a global time function, and so on and so forth. There are different conditions that you can impose. And the one that it seems the strongest that we can impose is the global hypervelocity. That's the space-time makes Cauchy surface, this motion of the universe at any single time. And again, there are interesting results here that this requirement is equivalent to saying that the topology of the space-time is Cartesian product of three hypersurface with this time. Okay, so it seems that global hypervelocity and the initial value formulation of GR is the natural, necessary framework for non-humanism, or this non-humanist conception I'm considering here. And for instance, Morning is taking a heavy use of the notion of Cauchy surface and the initial value formulation for grounding physical possibility in general and counterfactual traits. That's what I'm going to discuss in the second part. So we see here, it's interesting because although the whole mosaic is not taken as primitive in this conception, and this again taken as a good feature, it seems that these conceptions have to acknowledge some kind of global features of the whole space-time. Even if somehow they don't want to accept the whole mosaic. Maybe, and then the question is, what's the status of these global features? Maybe as constraints on the world. And moreover, it seems that there's a tension with, you remember this local grounding of law and causation, what is sometimes called the singularist spirit of dispositionalism. The fact that in order to make sense of law of nature or causation, you don't need to look at all the regularities encoded in all space-time. That can even C typically is the cause of the E in these conceptions. Not only depend on the nature of C, as in standard non-human conception, but it seems here also on global features of the whole space-time structure. So there is a kind of tension here with the typical singularist spirit of these conceptions. And in the case of humanism, humanism seems a little bit more flexible because it can seem to be this feature seems to be easily accommodated for in humanism, just as aspects of the mosaic. Okay? But even if we take the human analysis of laws to be best articulated in the context of the initial value formulation at a whole, for instance. These global aspects can be just merely taken as aspects of the best system. But there's interesting questions here. Maybe we have two distinct analyses of laws in causation. One type of analysis in global hyperbolic spacetime, where we have this initial value formulation context or framework available, and maybe another one in non-global hyperbolic spacetime where we don't have this initial value formulation available. And there are questions also about supervenience. How exactly do these global features supervene on the mosaic? Clearly, there is no local supervenience. It's locally everything look the same, even if a global topological feature could be different into space. Okay. This is for the first part. Now, the second part, I'd like to more specifically look at the notion of counterfactual in the dynamical context of GR. And this is very recent work in collaboration with José Luis Carrillo from the University of Bourgogne. And the idea is to look at counterfactuals in the framework of the initial value formulation of GR. And again, this is not completely academic. We've seen that it does play a role, and that I'm going to discuss, in a natural role in the way we evaluate counterfactuals. And it's related to the topic of laws of causation, clearly, because there is this kind of intuition that typically laws of nature support counterfactuals. And the conception that we may use counterfactuals in order to evaluate causal claims, and so on and so forth. So there is clearly a strong link there. But the idea here is to show that the dynamical nature of space-time may raise difficulties for evaluating the truth value of counterfactuals. And Eric Cooley ultimately has discussed this general idea that since we don't have a background structure in GR, since that we don't have a structure with respect to which counterfactuals can be evaluated in the dynamical setting of GR. And typically what he's considering is the counterfactual claims of the type, what would have happened if such mass would disappear in space-time. Okay? What would have, if the sun would disappear, then the planets would behave so and so. This kind of counterfactual would make perfectly sense in Newtonian theory, but in GR it's not clear. And typically, he relies on the fact that the limiting family of Schwarzschild space-time parameterized by mass reaching to zero, okay, so the mass disappearing, the sun disappearing, has no unique limit. Okay, so you cannot evaluate this kind of counterfactual in GR, it seems. And this is clear, intuitively. Typically in GR, it's related to the fact that the vacuum solutions are not unique in GR. So there's no unique vacuum solution. So it's not clear how to evaluate this kind of counterfactuals. But here, I'd like to focus more specifically on the initial value framework and the difficulties raised in this framework. It's of course related to the dynamical nature of space-time, but it's more specific. And it's natural in this sense, because typically one way to understand the antecedent of the counterfactual, the common, if you want, of the counterfactual, if blah blah blah, a natural move is to understand this in terms of modification of the initial data. Okay? This is intuitive what we do all the time, and this is exactly what's modeling proposed. Here's from his first chapter of this relativism physics book. Here's the kind of counterfactual he's considering. If the bomb dropped on Hiroshima had contained titanium instead of uranium, it would not have exploded. How do we evaluate the truth value of this counterfactual? We propose 3 steps. First step, choose a Cauchy surface that cuts through the actual world, so continuous at an instant time, remember, and that intersects the bomb about the time it leaves just before the counterfactual one to bear. All physical magnitudes take some value on the surface. Okay? Step 2, this is a crucial one. Construct a Cauchy surface just like the one in step 1, save that the physical magnitudes are changed in this way. Uranium is replaced with titanium in the bomb. Okay? So you just modify the Cauchy data in the right sort of way. And step 3, allow the laws to operate on this new Cauchy surface with a new boundary values generating a new model. In that model, the bomb does not explode because we have now titanium. Ergo, if you've got the laws right, etc., the counterfactual is true. Okay? This is a clear receipt how to evaluate the counterfactual claim according to more data. Of course, here, for him, it's an argument what kind of role the laws are playing. Okay? But the crucial step for us is the step 2. Construct the Cauchy surface just like the one in step 1. Just like the one in step 1. Okay? Say that the physical magnitudes are changed in the right sort of way. And there are 2 crucial ingredients here. First, the Cauchy data need to be modified in some unique way. Okay? And second, that there is tacit ceteris paribus condition. Leave everything else the same on the Cauchy data. Don't change the Cauchy data somewhere else, okay? Don't change the speed of the plane or and so on and so forth, this kind of things. And again here is, we may lack these ingredients in GR. Now, and this is the codification in the physical theory is the initial problem in GR. And the main issue is how can we specify appropriate initial data in GR. This is a physical problem. Okay? Very important one. Natural initial data in the 3+1 formulation of GR is typically the 3 metric on a 3 hypersurface, and the second form, the extrinsic curvature on this hypersurface. And then the idea is that these are intuitive, good initial data that you can evolve and you get your spacetime, your four spacetime. But now, given a formulation, then if you do this, the actual equations can separate into 4 constraints and 6 evolution equations. And then your initial data cannot be fully specified. Okay, they have constraints. They have to satisfy these kind of constraints. Here, they're just counting the vacuum equations, no matter for simplicity. And but first, before solving these constraints, a meaningful question is: does all this make sense? Do these constraints have solutions? Okay, are they unique? Typically, a genuine question. And there is this very important result in GR due to Choquet-Brouillard and Gerard and others, then the refinement of this theorem, that for any smooth set of initial data of this type of just mentioned, satisfying the vacuum constant equations, there is a unique diffeomorphism, maximum normally hyperbolic development. Okay? So this is just a space-time corresponding to initial data in a smooth way, basically. This is extremely important result. Gives you existence and unicity. If you have this, you can start to do things. Very important. But now, these very important results, it's actually a set of results, do not say anything how to specify the initial data. Okay? Just tell you that given initial data, then you have the existence of a solution for these constraints and unicity. But they don't tell you anything about how to construct this initial data. But of course, the specification of this initial data, this is a crucial issue, okay? Making predictions typically. And for us, for evaluating counterfactuals. And as I said, the constant equations are underdetermined. There is some freedom in choosing the components of the trimetric and the exclusive curvature, which are constraints, and the ones which are fully specifiable. The one you can fully choose, and the ones that are constrained by the constant equations. And again, this is a critical issue for applying this theory. In our case, for translating, if you want, the antecedent of a counterfactual into initial data, step 2 of modeling. Then, in order to evaluate and then check whether the counterfactual holds or not. And there are now there are several strategies to solve the constraints. The main one is just to find a decomposition of into a constrained part and a fully specified part. But again, there is no unique decomposition. It's kind of a gauge thing if you want. And there are two main types of decomposition: the York Dictionary conformal decomposition and the so-called conformal thin sandwich decomposition. I'm not going to go into too many details. I'm just going to continue the first one, just to try to pin down what exactly are the features in this decomposition, the constraints that might pose problem for evaluating counterfactuals. And then there are the gluing techniques. Okay, very important. I'm going to discuss this in a little bit. It's the idea that you try to put pieces of solutions together in order to build a new solution. Okay? This is quite intuitive, but it's complicated in GR. Why? Because it's not linear. Okay. Your traditional is conformal decompositions. This is the standard decomposition. That's typically what you would use more or less, at least this kind of family of conformal decomposition in order to do predictions for a black hole merger and gravitational waves and so on. The general idea is to split the initial data into a free conformal data and constrained data, such that for choice of free data, okay, the antecedent of your counterfactual, then the constraint equations turn into the determined elliptic partial differential equation system that you can solve over the constrained data. Okay, it's really important. This is trying to convert the geometric equations, okay, the constraints I've shown you, into analytic equations that you can solve. Elliptic equations, partial differential equations. Typically, what you do, I'm not going into the details, but the idea is you make a conformal decomposition of the 3 metric, okay? It's conformal factor, conformal metric. This is what you can really specify. Okay? And then if you do this, the Hamiltonian constraint, one of the 2 constraints, becomes an elliptic equation for phi here. This kind of form, elliptic form. Laplacian corresponding to the conformal metric. Okay? And there's also a transverse traceless decomposition of the extrinsic curvature in terms of a symmetric transverse free divergence free tensor as a free data. Okay? And then the momentum constraint also becomes an elliptic equation. I'm not going to go into too many details, just want to focus on the non-linearity and ellipticity of this. Non-linearity, again, it's crucial here because it's the root of all difficulties somehow. Because you cannot just add two solutions in order to build a new one. Okay? And in particular for us, you cannot just add a small perturbation to known solution. Okay? The modification linked to the translation of the antecedent of your counterfactual. Because the perturbation added to your known solution, Schwarzschild or whatever, is not going to be a solution because of the non-linearity. But you not only have non-linearity, but you also have ellipticity. What does it mean? It means that you have some kind of global aspect to your perturbation. Because the antecedent of a given counterfactual cannot be translated in terms of a freely specified data. It's typically here the three metric, the conformal three metric, without affecting the whole three metric, the physical one. This is the physical one. Okay? This is a conformal one you can freely specify, and then you get the physical three metric, the physical initial data through the conformal factor, which is the solution of the elliptic equation. Okay? But the elliptic equation is a global equation. Okay? It's not a hyperbolic one. It's not about the evolution of initial data. Okay? Kind of steady state, if you want, equation type. Typically a Laplace equation. And this is very important because when you're modifying something, your small perturbation, changing the uranium with titanium, in GR you're actually modifying everything on the three surface, okay? In a not uncontrolled way. So the combination, this is very important, the combination of these two creates trouble. Remember these two crucial ingredients involved in C. The Cauchy data need to be modified in some unique way. Here I added prescribed. Okay, what does it mean? Because of course you can modify the initial data, and the Schocker-George theorem tells you that you're going to have unique solution. But here, what you want is you have a prescription, the antecedent of the counterfactual. Okay, and you have to translate this in a unique way in terms of the modification of the initial data. But here, this is exactly what seems to be lacking in GR in general. Again, because of the non-linearity combined with the ellipticity. And Catenac's Paribus condition, leave everything else the same. Don't change the plane, the things, and so on. The atmosphere, okay? Law of gravity. Again, we may lack this because of the ellipticity, the elliptic structure of these things. Again, combined with the non-linearity. Morlin actually considers this kind of trouble. Well, here's what this. Let us call any physical magnitude which is unchanged when we apply step 2, okay, changing uranium to titanium, uninfected. Those which are changed are in both the original and new data sets infected. This distinction may be quite clear in some theories, in others, notably in certain quantum states, the physical magnitudes may not be localized and may not be so entangled that the infection cannot be localized. In such cases, our intuitions break down. Okay? And here the end is that it seems to be not only a quantum issue here, but also an issue arising in the GR context. Because again, of the non-linearity and the ellipticity, the elliptic structure of the constraints, due to the dynamical structure of space. And it's a concern also for other accounts of counterfactuals, of course, such as Lewis. Okay? Remember Lewis, this idea of possible worlds. It's not clear how to define the nearest world in Lewis settings. Okay? This is kind of the notion of small miracle, just a small thing, small miracle, the same here, roughly. In GR, it's not clear what a small miracle amounts to. Okay? Small miracles, again, in terms of initial value, would mean you change slightly freely specifiable data, like the conformal factor, the conformal metric, without changing the rest. It has to be a small miracle in order for your world to be close, according to Lewis. But in GR, it seems that in certain cases, at least, we cannot do this. Okay? So the whole setup seems to be more complicated than that. Okay. How do you do with this time?
How much more do you have?
Have 10 minutes more? Okay, very good. Thank you. Again, I want to emphasize this is a crucial issue for making predictions. Okay? GR and numerical GR. Typically, again, think about black holes. These great results about gravitational waves. We have certain observational astrophysical data. We want to translate them in terms of initial data, run our computers on numerical algorithms, and then make predictions. But here, it seems to be not that easy. Again, of course, in certain cases, and this is also something incredible and beautiful in GR. It seems to be possible, okay? Thanks to linearization, effective prediction, and again, it's beautiful, this result. You can predict gravitational waves from black hole merger to this degree of precision. It's just amazing. Okay? But here again, we have in principle arguments that this may not always work. Okay? In a certain sense, black holes are extremely simple objects. Think about cosmological setting, things might be more complicated than that. And I want to emphasize this is an area of active current research in the foundations of GR. And an example, typically try to bypass this idea that because of non-linearity you cannot add two known solutions to create a new one. But there is these gluing methods. Okay? This is also an area of mathematics, geometrical analysis typically. But here in GR, I'm not going to, this becomes quite complicated at some point, but just to give you an idea of recent work, there is this method of asymptotic exterior gluing. It's a beautiful term by Corvino, I'm sure. Typically, one can smoothly glue an interior region of an asymptotically Euclidean solution to an exterior of a slice of a Schwarzschild or Kerr solution. What does it mean? It means that you can change things in the interior of your mass if you want to. But from far away, still looks like Schwarzschild or Kerr. Okay? So it seems that it helps typically for our counterfactual problem. But of course, it's tricky, and typically at the transition zone, things might go wrong, or at least, yes, not true. And more interestingly for us, there is this connected sun gluing methods. Typically, due to the number of people in the foundational GR, and very crucial in these people, for any chosen set of n asymptotically Euclidean solutions of the constraint, of the black holes, stars, one can construct a new asymptotically Euclidean solution which includes interior regions of this n chosen solution placed as desired and with the desired relative momentum. This is very strong to some extent. Okay? You can put things together and create a new solution satisfying the constraints. But of course, there are caveats here, and you should be careful. Typically, the distance between the body must be sufficiently large. Okay? But I mean, this is really an ongoing area of research, and it's not, yeah, how far we can go is still unclear, I guess. But just to give you a flavor of these beautiful results. Now, for this part, evaluating factual, in particular using models received, and in GR is not impossible. Okay, typically we can use maybe these gluing methods, but far more subtle than commonly thought. And typically it may be well the case that in some GR contexts, none of these techniques work. Okay? Typically maybe the very initial value formulation may not be appropriate. And a lesson for quantum gravity, here there is an intuition, okay, that investigating the foundation of one of the ingredients theories, here GR, may go further for understanding quantum gravity. And here, the relevant aspects could be about, and I think we should work on this, about the limitation of the initial value perspective, okay, because of the intrinsic temporal aspects somehow. And maybe more fascinating, these kind of analogies. Remember this notion of infection in modeling. Okay? It's more or less clear in the quantum case, but here seems to be an analogy also in the GR case. Okay, part 3, it's going to be short here. Laws and causation now with no space. Okay? We're specialists about this. The research program in quantum gravity suggests space-time relative somehow. So what about laws? The standard conceptions of laws and causation in this space-time less setting? It seems that just not appropriate, maybe obsolete. The obvious question is, can they be generalized in some sense? Very roughly, just give you hints how this this ongoing work. Maybe we can generalize this notion of human mosaic. Here, the humanism seems flexible enough. Okay? Non-temporal, in terms of non-spatio-temporal distribution of all the facts at the quantum gravity level, in some sense, as described by the theory, so should be clear. In terms of abstract spaces and graph groups, such as spin-equals forms, causal set group manifolds. Okay, you have these abstract spaces, and you take this as the mosaic. And then quantum gravity laws just as generalized notion of patterns in this generalized mosaic. To be an idea. And this kind of it's interesting to see that this kind of strategy has been already implemented in the foundation of quantum mechanics, or the ontology of quantum mechanics. Okay? Moving from space-time typically to configuration space. Barry Lower is one of the proponents of this, where he argues that the relevant mosaic for the human conception should be the configuration space in the quantum context. Okay? So the space where the quantum functions become. For primitivism, it seems that the challenge here is to spell out a little bit this notion of production and learning aspects in non-spatial temporal terms. But as we've seen, it seems that there is some kind of intrinsically irreducibly temporal aspects to it. Maybe through some kind of irreducible non-spatial temporal modality. So here the trick could be to look for some kind of non-temporal quantum gravity dynamics, okay, in terms of transition amplitudes or quaternary states, or in terms of generalized phase transition, non-spatial temporal phase transitions. And these phase transitions would maybe give you a notion of production of learning, as this is stated by these conceptions. Okay, I conclude now. I've discussed the spatial temporal aspects of this kind of human and non-human conceptions. I hope to have convinced you that in the GR context, these conceptions might need to be adjusted, typically because of the global topological constraints that one might want to impose, and that maybe the humanism is more flexible in some sense. There is the issue of how to make sense of supervenience of the global features there. And then in the second part, I've discussed the subtleties due to nonlinearity and the elliptic structure of the constraints in the initial value formulation of GR for evaluating counterfactual frames. And this is rooted in the fact that spacetime is dynamical. So no background with respect to which you can evaluate these counterfactual. And just at the end, I've given you a few hints about how to generalize these conceptions about law and causation in the quantum gravity context. Thank you.
Okay, thank you very much. Let's change the setting here and then first ask whether there's questions in Chicago.
I have a question.
Just a second.
Can you hear me okay?
Yeah.
Okay.
Yeah, sure.
Very
Just a
nice.
second.
But thinking about the business of counterfactuals in general relativity, it seemed like from the past, I didn't remember Maudlin talking about that, but it looked like from the passage that you quoted that his attitude was there's some kind of pragmatic aspect of counterfactuals, and in these cases the correct responses, they just aren't defined, but that's okay, right, because of this sort of pragmatic aspect. We just don't know what we mean in these cases. But I wondered if you thought there was something stronger that could be made out of the failure of counterfactuals. Because earlier in the talk, you were making it sounded like there were going to be stronger connections between time, laws, counterfactuals, the production. So what do you think? Is there a problem? Is that just an interesting fact about counterfactuals in this context, or is it some problem for the more primitivist notion of laws?
I think I think you're right. I think modeling is quite pragmatic with respect to this. But first of all, I think he was just thinking about the quantum case. So here it might be a more generalized in some sense, not only the quantum context, but also the GR context, where we might have problems in evaluating counterfactuals. And then I think, I think it's part of, typically for modeling, it's part of the strategy of saying, okay, we take laws as being primitive. Might not sound that good at first, but then, hey, I can show you all the work it can do. Typically in supporting counterfactual claims. But if actually this temporal evolution view of laws is not so explanatory powerful after all in certain contexts, and typically GR would be one of them. Yeah, I think maybe it has implications. Yeah, I think so.
Okay. Just to be clear, I mean, so the sort of Humean account of counterfactuals looks pretty similar though, right?
Yeah.
And at least we take that from Lewis. All right, so it's not, but it's more like there isn't any special advantage to the primitives, the counter laws in this case.
No, exactly, yes. And again, I think it's due to the very structure of GR as a theory, because it's not explicitly a theory about the evolution of something. You have to do a lot of work to transform the fundamental dynamical equation of your theory in terms of something evolving in time, maybe the initial value formulation, and then you have these very specific features which show that things might not be as simple in order to evaluate counterfactuals.
Right. Thank you.
Okay, Arnold.
So I'm considering this from a more complex systems point of view, but this Tim Modlin, now this one is about. Yeah. So he was there at the emergent quantum mechanics as well, and he discussed laws in terms of entropy and more descriptive laws in my point of view. Does he make in the book a distinction between different kinds of laws, like interactions as a law, or symmetry constraints as an energy conservation law, or a descriptive law as field equations?
Yeah, I think he does mention this, but for him, an important category of, or set of laws are typically these laws of dynamical evolution.
Evolution.
Yes. These are critical. And of course, you can also say, okay, maybe GR is not a case where you have such laws, but GR is one of our fundamental theories. So if you have to say something about what kind of law-like entities you might have in GR and so on.
Because in this pre-space-time, which you mentioned at the end, I would expect there to exist some kind of interaction law between pre-space-time entities. But for a descriptive law, you have to add like an absolute space-time or something that is out of the system to describe the pre-space-time system. So there might be difficulties there in the what you say is your general view on laws and what you can say about
I think you can generalize the notion of interaction as well. Typically, the part of the loop quantum gravity people, that's a little bit the way they talk, kind of fundamental interaction notion and relativity.
Yeah, I agree about interaction
notion.
Okay. Thanks.
Baptiste.
Okay, so thank you very much. So my question is about trying to have a better understanding of what you did, and in particular how you argued against the two kinds of non-humanism, so primitivism and dispositionalism. So, as I understood you, you were kind of arguing against the two positions at the same time, and that you had one argument based more on time, and another argument based on global features of space-time. Is it kind of right?
Yeah, more or less. The thing is, first of all, I don't think I was really arguing against these concepts. The other thing is, if you put them in a general context, then it seems that you have to acknowledge these global features of space-time, and then this raises new interesting questions: how to make sense of these organizational features in this concept. And I think this is also an interesting question for humanism, typically. In some sense, it's more flexible because you can say just it's a feature of the description of the whole thing. But on the other hand, if you look more carefully at the notion of human supervenience, I don't know, it might not be that easy to make sense of these global features as being supervenient locally or at least locally in one world.
Okay, I mean, just leaving, I agree on the last part, but just that my feeling was that the argument based on time or the considerations about time were more against, could be put to work more against primitivism, and on the other side the arguments based on global features of space-time could be used against dispositionalism. So I had the feeling that the two theories were different and people have separate the two and use in one sense against primitivism the idea of problem with having one Cauchy surface, so against primitivism in this way, and the problem with dispositionalism was more related to the problem of finding local dispositional properties.
Yeah, you're right.
So I think it's maybe
that's a little bit the way I've presented. You're right, and especially given the fact that Modin explicitly emphasize the role of time alongside the role of the laws. So in this sense, you're perfectly right. But on the other hand, this very notion of production also linked to this position. This clearly seems a temporal connotation somehow. Maybe you can generalize and have non-temporal dispositions.
But it's my second point. I mean, most people argue that if you have a dispositional theory, you need to have this notion of production.
Yes.
But it's not clear. I mean,
no,
why not having a closed time-like curve with a circular properties bringing about the other properties? I mean, I think it's still consistent. So it's why I think for dispositionalism, I would say the most pressing problem would be the locality.
Yeah, you might be right. Actually, I've presented part of this talk in front of more metaphysically oriented people or metaphysicians really. And some of them were not really shocked in the sense that exactly what you said. Yeah, you're right. Exactly. Yeah. But it seems just, on the other hand, that it's not something which has been explicitly discussed in the metaphysics. I'm not aware. I'm not sure, but that's what these people seem to say. And yeah.
That's the position.
Yeah.
Lorenzo?
When you say that there is a problem in evaluating counterfactuals, sometimes I'm not sure whether you mean that there is an epistemic problem in coming to know whether they're true or false, or whether there is a problem with the usual definitions or with the usual truth conditions.
No, very good. No, the problem is, very good, thank you for the question. The problem is, first of all, epistemic, clearly. Because on the ontology side, it seems that everything is secured by the kind of extremely strong results I've shown, like the Schotte-Breuer-Gerock results. Okay, so you have initial conditions, then you can say, if the other assumptions are fulfilled, then you have existence and unicity. Everything is fine. But the problem is at the epistemic level, how to translate prescribed data or command or antecedent of a counterfactual into initial data. This is the worry. But once you have initial data, everything is fine. But the question is the meaning of the data if you want, and the link between between what we want to do, what we observe, and the typically very specific initial data that we have. Typically here in this decomposition, the conformal metric and the symmetry, the symmetric tensor and so on.
Yes.
So this translation between these two is.
But maybe wouldn't you say that even if the equations were linear that you had to solve, and say all of this problem went away, and you had say the simplest possible case, wouldn't you think that the recipe that modeling gives is in any way idealized and could not possibly, be followed anyway?
It's idealized, but here I think this is a good question. I have to still work on this, but I think there's a qualitative gap. This is very good. I think if you have a linear theory, then you might have approximation issue and so on, but the problem is entirely different. Why? Because again, you can add perturbations, small perturbations, and it's in certain conditions, it's again a solution of your constraint of your theory. Okay, this is entirely different. And actually, we are working. That's the idea of José Luis, making this kind of map of theories where you have non-linearity, ellipticity, so you can consider theories which are non-linear but without this elliptic structure. Okay, and an example of this is typically Nernström theory of gravitation. Okay, you don't have the constraint part. It's a non-linear theory of gravitation, but you don't have the constraint part. You can think of theories which are linear somehow, but with an elliptic aspects. Okay, I don't know, theories which include Laplace equations, I don't know, electrostatic, I don't know, and or Maxwell theory, or you can think of then GR, nonlinear and elliptic structure. Okay? And you see, if you think about these examples, you see that what poses problem here is the combination of nonlinearity and these global aspects linked to the elliptic structure of the constraints. Thank you.
Niels.
So it would be postponed for a moment.
Okay, so I have a question. This came out in your answer to Nick's question about, in a way, the Humean being in the same boat as the non-Humeans as far as counterfactuals are concerned, because it seems like a general problem in GR on any metaphysics in a way, to get a good handle on them. But maybe there is some hope for the Humean, where it's not obvious that the non-Humean can have the same hope reasonably. So one natural way for a Humean, I guess, I would have thought, would be to abstract away from this idea of an initial surface that you manipulate and then have the production going in some different way and see what happens. But look at the whole thing instead. Look at the space of nomologically possible relativistic spacetimes and look at the structure in that space. That space has a topology, which gives you a similarity structure somehow that you could use perhaps to say this spacetime is more similar than that spacetime, and you can do maybe something almost like a Lewisian analysis like that. One problem if you do that, of course, then this will sensitively depend on the topology that you impose or that you assume for that space to be the case. And there's work, as you may know, by Sam Fletcher, which shows that there's justification for different topologies, and some of these things come out wildly different than any measure of topology.
No, I think you're right, and I think you couldn't think about making this kind of move and then classify according to the different topologies you're considering. I think I think you're right, and to some extent that's what I suggested. Maybe there is this intuition that humanism is more flexible in this sense. I agree, and at least to the extent that it's not tied to the initial value framework. I think what you said is correct, and I would agree. But still, I think the difficulties remain in the sense that precisely what you said, evaluating the similarities is precisely the issue here. It's not clear how to do this in a general sense.
Well, I mean, you could say we accept that it's sort of context dependent, or because, you know, given some contexts, given some sort of theoretical aims, there may be justification to use this topology rather than that, and then if you impose some additional conditions for which there may be justification, then you get more of a handle on the problem.
Yes. No, this is a possible move. It's just, again, striking and interesting that even the prominent unions like Nebel have made this move towards the initial value formulation, because it's extremely intuitive and powerful. That's the way we work, that's the way we make predictions, that's the way we evaluate counterfactuals intuitively. And the fact that there is some resistance in GR, I think it's a very interesting fact, and I think it's true. It has consequences for both unions.
Of course.
They have maybe to change strategy, and of course for primitives and dispositionalists, of course, yes.
Yeah, no, I mean, it's a very natural move, no doubt about that. And if you look at pre-general relativistic theories in physics, they were all formulated in the sort of basically that general template.
Yeah.
You have a set of initial conditions which are permissible variations of how things could be, what the state of the physical system at the time could be, and then you have some dynamical laws.
Yes.
Yeah.
And again, if I remember correctly, this distinction or this framing of the best system, Lewis best system analysis in terms of initial value formulation does some work, some metaphysical work for that work. So it's fixing problems. So if you drop this, it would be interesting how you fix these problems in a different setting. So it's not for free that he's doing this.
Well,
again, remember, if you think about a system where you heavily constrain the possible initial conditions, it seems that you have huge informativeness in Lewis sense. But what's the cost? Okay? You don't want this. This is bad informativeness. This is bad. It's bad model because you're just restricted the initial conditions allowed. Okay? And think again, there are these famous examples in cosmology. Okay? You don't like this if you have very specific initial conditions. You like a more dynamical explanation. And in general, physicists work this way. If you have a dynamical explanation for the very specific initial conditions, this is taken as a good feature. Okay? So it seems very natural. Anchored again, that's back to molding argument in general. That it's really deeply anchored in the way physicists and scientists in general work. And here it seems again there is some resistance from geologists. I think it's very, very, very interesting.
Niels?
Yeah, I was just wondering, since you were mentioning gluing, right?
Yeah.
People doing work on it. How much is there a theory about this gluing? I mean, how many different versions of gluing space?
Yeah, it's a whole field. It's extremely interesting. There is the field in geometric analysis. This is a field in mathematics, and now there is this growing field in GR, and it's really fascinating. There's a lot of things there.
So is there after all a high flexibility in gluing?
Sorry?
So high flexibility in gluing things together, you would think, or is there high?
There are many open issues there. How far you can go, how many assumptions you can relax. Typically, these Euclidean assumptions. There are many issues. Really, it's ongoing work. It's difficult to judge, but I think it's very promising.
So why Euclidean assumption? Isn't it typical? Sorry, we talk about slice space.
Yeah, but you could imagine
slice space.
Yeah,
okay. Then.
Sorry.
Yeah.
You can typically imagine a cosmological context where you would not like this kind of assumption.
Exactly, because it's just, for the foliation, it corresponds to having absolutely flat space.
Yes, for foliation.
And
then, moreover, you want this to remain under time of rotation.
Yes. Very good. Yeah, I'll ask you more.
Yeah.
I have one more question. So the Choquet-Garrosh result is, of course, very important and very powerful, but it also has limitations.
Yes.
It's for vacuum spacetimes, if I remember correctly.
No, I think there are generalizations to space-time with matter. I think maybe Maxwell, Einstein, these kind of things. I think at least there are generalizations.
Okay, good. That is important, obviously, because we don't want a theory that only applies to to cases where there is nothing
Yeah.
substance.
Yeah, of course. And these people, it's very interesting that because the more or less the same set of people, these people have worked also to the issue of the solution of the constraints with minor. What's the structure of the space of solution of these constraints? And here there are many results also.
But here's another concern. You said that given it, this sort of the ontological problem is solved because it guarantees existence and uniqueness, but it guarantees existence and uniqueness under some conditions. I forgot what they are, but these are global conditions too. Right?
Yeah, of course you have global hyperbolicity,
And so-
this is for sure, and you have this kind of regularity conditions on the metric, and the second one on the form, and then your space-time should somehow depend smoothly on the initial data, this kind of things. Yes, exactly. Yes.
So there are concerns that
Yes.
that really complicates the picture again when you think about it, because again, the counterfactual, even in those cases, the existence, the unique existence of the evolution is then hostage to additional
Yes.
somehow imposed conditions, and that seems to be
You have to take this into account, clearly.
not very pleasant when you want to give it.
Clearly. But at least here, given these assumptions, we have strong results.
Sure.
And the type of worries I was raising, I think, which are really serious worries, are of the epistemic type in the context of Lorenzo's questions, rather than ontological. Which doesn't mean that there are no ontological issues at all. That's not what I said. But I think again, the take-home message is really that there is this epistemic worries about how to make sense of counterfactuals and predictions in GR. And I think that again, it's the working physicists in GR are aware of this. It's really and there are two sides again. There are these difficulties, and on the other side, there's this magic. You can make approximation, linearization, and make this incredibly powerful, precise predictions. If you look at the mathematical structure of the theory, the fact that it allows this as precise rules, and it's somehow surprising. All this to say that there are a lot of things to learn from the structure of GR.
Yes, was another question.
Just very shortly, so I do understand, of course, that the several flat space-time several vacuum space-time solutions, right, in GR, but difficult intuition why, in the case of the Schwarzschild space-time, the limit is not unique. I mean, even if there are several vacuum space-time.
Eric has made a-
Exactly, but is a good intuition, is a simple intuition behind that?
I think that's the two of them. The general one is the fact that you don't have a fixed background with respect to which you can consider as a Newton case, with respect to which you can consider the case where you have the sun and the case where the sun is disappearing.
Yeah.
In a Newton context, we're considering these two cases with respect to the background, same background space, so there's no ambiguity in evaluating the counterfactual. But in the GR case, you lack this. This is the general perspective, and the more specific perspective, I think it's linked to the lack of uniqueness of the vacuum solution. No? The fact that if you're shrinking the mass to zero, it seems that you cannot get a unique limit because there's intuitively several possibilities of vacuum solutions. No?
You think so, but especially since you take the limit, you would think that you kind of continuously walk perhaps towards one out of these options, right?
Yes.
So, no.
No, for this, you're right. No, for this, I don't have a clear intuition. I mean, the fact is pretty straightforward.
Yeah, okay, no, I'm just wondering.
The calculation seems clear.
Yeah, no, just wondering.
No, but I don't have additional intuition for this.
The uniqueness of this is, however, not guaranteed. It's not obvious. This will always be guaranteed. Get to one.
Yeah, no. It's
but I don't have an additional physical intuition for this.
Okay, no, just sorry.
I have another question. So, some of these problems, in a way, arise because we think of GR as sort of a little bit too globally, as it were, too much as a sort of a cosmological theory. Maybe we should just give up that idea and think, no, GR really is an extremely good theory for well-confined, regional, I say, to avoid local, regional or regionalizable gravitational systems and some of their interactions. And those things, we have a very good control over that. So we do numerical gravity, we can have very, very precise predictions about the merger of two black holes, and we can meaningfully ask questions. What would have happened if this black hole would have had one solar mass more than the other?
No.
No?
No, that's the point. No. From a mathematical relativist point of view, you cannot do this. You cannot put the black hole somewhere else, you cannot change the mass, you change everything.
But numerical relativists do that.
Yeah, they do this, but it's contrived and
But they're extremely successful.
But for different reasons. You see, it's for different reasons. You do this for different reasons. I'm close to what you're saying in the sense, it's what you said at the beginning is very close to the spirit of these gluing methods somehow. You look at things.
That's true, yes. You think
together.
you can then glue this
Yes.
to the rest of the
Yes,
universe.
but again, look at the difficulties of doing this.
Yeah, no, I appreciate those. But suppose bracket those to gluing difficulties for a moment. Just look at your system of two black holes. This is what numerical relativism is.
But again, it
It's
involves
like they vary the mass, they vary
Yes.
the relative
Sure.
momentum, and how they actually.
But you cannot do this,
down.
strictly speaking. It involves.
But they're good. They're pretty good.
Yeah, but what is underlying this is a kind of effective understanding.
It is, absolutely. As a
And this
fundamental
might-
global theory, you have all these principal problems.
Yes, but this-
if you give up that aspiration,
This might break down in other contexts and not as simple as black holes. Think about systems with genuine material structure.
like any
You cannot do this.
like any limited effective theory, non-fundamental theory, it can break down.
Yes,
So
but
that-
here the worry, again, this is all very complicated, but here I think the worry, the genuine philosophical foundational worry is that there is an in-principle, very peculiar limitation in the case of GR. Because the black hole case, again, is very specific, and again, even the fact that it works is somehow a wonder given the mathematical structure of the theory. No, really, I mean, it's not.
it is, but
And so, given all this, there is a high chance that in other contexts, these linearization effective description techniques, it will just break down.
yeah, well, I appreciate all your arguments and everything you say, but nevertheless, I can't help but be impressed by the advances in numerical relativity in the last 10 years or so, which effectively, fallibly have managed to really simulate things which 10, 15 years ago would have been considered.
No, sure, and I'm not denying this. On the contrary, I'm very, obviously, admirative of all this work. And as part of this foundational, part of the foundational papers I'm relying on are typically work from the numerical GR community. I mean, that's again, my message is that there is a lot of things to learn from this.
Sorry, I got a little bit carried away. No more questions? We really, final chance in Chicago.
No thanks. I like the questions that people ask. That was very helpful.
Okay, I mean, time is up anyway, so please join me in thanking Vincent again.